Excellent. All right. So, great. So there's one concept left, and that is how molecules look like in real space. Now, I had some balloons, but they've gone all over the room, and I don't want to get more. I can see if I can blow this one up without it blowing up. So molecular geometry is how molecules look in real space, and it's based upon the other half of the most important concept. If opposites attract, what do likes do?
Repel.
Repel. So electrons repel. And whether it's an electron cloud from bonding or an electron cloud from an unshared pair, remember unshared pairs, the two dots? Boop, boop. Those create what are called domains. A little bit bigger. All right, so let's draw water, because water is an excellent example of a molecule that's very simple and it's very easy to see its domains. So water has a central oxygen, and how many dots go around oxygen? 6. It's in group 16, so 1, 2, 3, 4, 5, 6. Cool?
Yeah.
Now around water, you're also going to find hydrogen. Now hydrogen has 1 dot each, so we're going to put hydrogen right here and hydrogen right here. And when we have those bonding dots, we're going to replace those bonding dots with sticks. Sticks or dashes or whatever. Sticks. Okay? Now that's our water molecule. Now hopefully you figured out, because you just took a quiz, that this is a very polar molecule. Okay? Now these unshared pairs are clouds of electrons. And these bonding pairs are also clouds of electrons. So there's a cloud of electrons, there's a cloud of electrons, there's a cloud of electrons, and there's a cloud of electrons. These clouds of electrons are called domains, and they want to repel each other. That make sense so far? So the principle that we use, in the tray, please. The principle that we use to determine how things look is VSEPR. As an acronym, VSEPR. And just as a little aside, an acronym, by the way, if you don't know what an acronym is, it's a pronounceable abbreviation. Okay? Like FBI is not an acronym. NASA is an acronym. CIA is not an acronym. NAFTA is an acronym. Kind of fun. Anyway, so like NATO is an acronym. FBI is not. So VSEPR is an acronym. Now this talks about how they repel. What do you think the E in VSEPR is?
Electron.
Electrons. And electrons always come in pairs. And what do electron pairs do? Repel. And where do you find those electron pairs? In the valence shell. So VSEPR is valence shell electron pair repulsion. And the idea is quite simply, dots or sticks are domains, and those domains repel each other. Now this third point down, or last point down here, where unshared pairs repel more than bonding pairs, this is not something we're going to deal with until, or if you take chemistry AP or more advanced chemistry later on. We're going to basically treat unshared pairs and bonding pairs the same way. Okay? Even though unshared pairs repel more than bonding pairs, we're just going to leave that out. So that's the idea. When you have bonds or unshared pairs, they are clouds of electrons, clouds of negativeness, and those clouds of negativeness repel each other in space. That's VSEPR. Make sense? Now, one thing that is important is that bonds or domains, doubles and triples still count as one domain. Okay? Double bonds and triple bonds still count as one domain. So, let's pretend this balloon is a domain, and this balloon is a wet domain, apparently, because it's in the sink. If you had two domains, and they wanted to get themselves as far away from as possible towards each other, what would they look like? Yeah, they'd look like that, right? So this is also this. I got these tiny little models. You can come up and play with them if you want. So this is what it looks like when you have two domains oriented as far away from each other as possible. If you were to describe this configuration, what would you call it?
Dumbbell.
Well, they're dumbbells. The domains are dumbbells. But if you were to describe how that one looks to that one, would you call it, I'm sorry, would you call it a triangle, a square?
A line.
You'd call it a line, right? And if we, linear, exactly. If we took line and turned it into an adjective, it would be linear. So if you have two domains, I'm going to show you a diagram here in a second. But if you have two domains and they orientate themselves as far away from each other as possible, they are linear. Cool? Yes. All right. Now what if you had a third domain? You had a third domain and they wanted to orientate themselves as far away from each other as possible. What would you call this shape?
Triangle.
A triangle, right? Like the Mercedes symbol is a triangle. So if you have three domains and they want to orientate themselves as far away from each other as possible, they make a triangle. But because this is a three-dimensional phenomena, they make a triangle in the same plane. So we call this trigonal planar. And I'm going to give you the diagram in a second. Well, you can show it how it's spelled. So three domains orientate themselves in a trigonal planar configuration. Yeah. And here's my favorite. If you have four domains, those four domains want to get as far away from each other as possible. And they make this crazy design called a tetrahedron. And I have some four-sided, oh, I lost a domain. I have some four-sided die which I'll pass out. These are four-sided die where each domain is at a vertex. It creates this crazy shape where it only has four vertices.
Pyramid.
Yeah, it looks kind of like a pyramid, but a pyramid is a four-sided thing on top of a flat surface. A pyramid is actually a five-sided shape. This is a four-sided shape, and it's called a tetrahedron. You guys have all played that crazy Russian game from when I was your age called Tetris? Tetris means how many lines? Four. Tetra in chemistry means four. So a tetrahedron is four. Okay? Now I don't have a fifth balloon. I had a fifth and sixth balloon, but they wandered away, so I'll just set this down. If you have five domains, oh by the way, this is what the tetrahedron looks like. Five is pretty cool. If you have five domains trying to orientate themselves as far away from each other as possible, you get this shape, which is a triangle plane with one on top and the one on the bottom. Are you ready?
Yeah.
If you have five domains, you get a triangle pyramid, a triangle pyramid, and a triangle pyramid on top of a triangle pyramid. So you get a double triangle pyramid. This is called trigonal bipyramidal. Yeah, that's the crazy one, trigonal bipyramidal. You don't see a lot, but you are going to encounter it now and then. And if you have six domains, which is the most you can have as far as we know, if you have six domains, you get an object that has six vertices. You get a three-dimensional object that has six vertices, and I'll pass these out too. An eight-sided die has six vertices. Yeah, a six-sided die actually has eight vertices, which is actually kind of hilarious. But an eight-sided die has six vertices. So this gives you a pyramid on top and a pyramid down below. So rather than calling it square pyramid by pyramid or something, they just call it octahedral because it makes an octahedron, an eight-sided device. And you kind of see how there's a side there, a side here, side here, side here. So if you have six vertices, you have an octahedron or an octahedral configuration. Want to see the diagram?
Yeah.
Like, that's what we're waiting for, buyers. Just give us the diagram. Come on, man. So these are the five fundamental geometries I'd like you to learn. Linear, when there's just two connected to a central atom. Trigonal planar, when there are three connected to a central atom. Tetrahedral, when there are four connected to a central atom. Trigonal bipyramidal, when there are five connected to a central atom. And octahedral, when there are six connected to a central atom. Okay. So if you're the picture taking or the note taking kind of person, I'll let you sketch that or take a picture of that before we go into one layer deeper. Let's go deeper. Now, when I say fundamental geometries, I will also call this electronic geometry because it focuses only on the electrons. All right, so far so good?
Yes, sir.
Now, how many domains are in the water molecule?
2.
Okay, I need a new
3.
spot.
How many domains are in the water molecule? Show me with your hands. You can see how many domains overall in the water molecule. Is there a 1, a 2, a 3, a 4? Hopefully you don't realize there's more than 4. So we got 4, 2, 3. Is that a 4?
Yeah.
4, 2. There's 4. There are 4. There are 4 domains in the water. 1, 2, 3, 4.
Oh, okay.
There's 4 domains in the water molecule. Now, does that make sense so far?
Yes.
If that makes sense, what is the electronic geometry of water? Right. Electronic geometry of water is tetrahedral. Okay? The electronic geometry of water is tetrahedral. But if you made water, and you did make water with the models, you made water, it doesn't look like it should look like. It doesn't look like that. In fact, water looks like that. Okay? Oxygen, hydrogen, hydrogen. What's up here?
Empty space.
2 unshared pairs, or lone pairs. So like an unshared pair here and an unshared pair here. They're kind of like invisible. So while the electronic geometry, are you paying attention? Because this is on your quiz, you're on your simulation tomorrow, your quiz on Friday, and your unit test next week. While your electronic geometry is tetrahedral, the molecular geometry is not. Molecular geometry. In your molecular geometry, 2 of 4 are bonding. Only 2 of 4 are bonding. Of those 4 domains, only 2 are bonding. So what would you call this shape? A V, okay. We could call it a V. It's not linear because it's definitely not on a line.
Parabola.
Parabola, okay. Well, chemists want to call it something simple. Because boomerang is too long, they're just going to call it bent.
Bent?
Get bent.
All their other words
Bent.
come up with
Yeah. Well, bent, simple, right? It's a bent geometry. It's boop, boop, okay? Bent. Okay, so it's bent. So water molecules have a tetrahedral electronic geometry, but a bent molecular geometry. Does that make sense?
Yeah.
Now, this is also kind of cool. If this is trigonal planar, if trigonal planar loses one of its domains and has an unshared pair there, it's also bent. Okay, so here's the diagram. There's your 5 fundamental domains. If you have 3 okay, try it again. If you have 3 domains and all of them are unshared, then the molecular geometry is also trigonal planar. So the electronic geometry is trigonal planar if you have 3, and the molecular geometry is trigonal planar if all of them are bonding, and bent if one of them is unshared. So this is the number of unshared pairs. Make sense?
Yeah.
Okay, you are going to encounter this in a simulation tomorrow, and then this is the last concept, so this is the last thing you're going to have to know on a test. Okay. So if you have 3 domains, it's trigonal planar. If all of those, the electronic geometry is trigonal planar. If all of those geometries, all those domains are bonding, then the molecular geometry is also trigonal planar. If one of those domains is unshared, the molecular geometry is bent. Question?
For stuff like the bromine fluoride thing, wouldn't all the fluorides also have their own things?
No. Well, yes and no. You only say it's geometry about a central atom. So you look at this, you basically say, what is the geometry about this atom? Which look like a rounded atom. Any other questions? Should we move on? All right. If you have four domains, the electronic geometry is tetrahedral. Electronic geometry is tetrahedral. If all of those domains are bonding, then you have a tetrahedral molecular geometry. If one of them is non-bonding, you get this interesting situation. This is not the one I wanted. Here we go. If one of them is, only one is non-bonding, you get a triangle pyramid. It's called trigonal pyramidal. So if one of them is unshared and only 3 are bonding, you get a trigonal pyramidal geometry. And if, like I said, for water, if 2 of the 4 are unshared, then it'd be bent. Bent. Make sense?
Mm-hmm.
Is this something you can handle?
Yeah.
I hope so. Okay. So again, tetrahedral if they're all bonding, trigonal pyramidal if 1 is unshared, and bent if 2 is unshared. Now, just like 3 domains has 2 possible molecular geometries, 4 domains has 3 possible molecular geometries, 5 domains has 4, and 6 domains has 5. But I'm not going to worry about you learning the molecular geometry for 5 and 6. Just realize that it has some, so just realize that. For this class, if you have 5 domains, they're all going to be bonding and it's going to be trigonal pyramidal. Does that make sense what I just said?
Yeah.
Okay. And if you have 6 domains, they're all going to be bonding in this class and it's going to be octahedral. Is this something you can handle? Okay. Now tomorrow, I'm going to show you what we're going to do tomorrow. We're going to start the class before you do our simulation, and we're going to look at the geometries of these things and whether or not they are polar. But we're going to start that tomorrow. Okay. So, let's go back to the original diagram, and then I'll ask you if there's any questions. So, 2 domains, linear. 3 domains, trigonal planar, or what's that called?
Bent.
Bent. 4 domains, tetrahedral, or
Some kind of pyramid.
triangle pyramid. If you say triangle pyramid, I'm going to give you credit. If you want to say trigonal pyramidal, that's fine. If you say triangle pyramid, you got credit. Or
Bent.
bent. Good. Okay. Okay, can you press the silver button again, please? Sure.
Bent.